All right. Are we live? We're live? All right. Hey, everyone. How much nicer is the weather today? Instantly, I feel so much better. Sorry? No, not talking to me. Weather's much, much better. Good to see you all. We're all feeling better. A Kahoot by UNSW. Wow. I guess I've spoiled the. Can I pause this? I'm gonna. Yeah. Cancel this. I'll do it in a second. Okay. Sorry. Let me do that again. So the good news, and I don't think it's any bad news. I think it's just good news. The good news is, well, the bad news is you all got, I think, destroyed on Monday. Does that sound right? With linked lists? So that's the bad news, I guess. The good news is that actually, that's pretty much the last sort of real piece of lecture content for the course. So the idea, well, there's a few ideas here. Usually in some terms, we get impacted by a few public holidays. We only had one this term, so we're a couple of lectures ahead anyway. But the general idea is we try and push a little hard so that we have a few weeks now where we can sort of let these topics sink in, recap anything that's caused issues, recap anything that you're rusty on, to help set you up, well for assignment 2 in the exam. So we're pretty much in a bit more of a flexible part of term now. Not to say that the lectures aren't important or there's no new topics or concepts. There's still important things to talk about. But we have a bit of flexibility now to spend time on what it is we need to spend time on. So I thought I would set up a little Kahoot for you guys to start dictating what it is that we spend the time on today and for the rest of the lectures. But there are a few lectures that are still set in stone, and I'll talk about those after the Kahoot maybe. So I don't know how well this is going to work, but basically just think of this as what do you want to do today? So we can keep talking about linked lists from a conceptual perspective. So go through whiteboarding, go through code writing, go through why they're useful. Typically, this lecture would be a linked list demo. We can talk about arrays. We can do like a broader demo with multiple topics, but this will obviously mean we have less time to talk about linked lists in particular. We can just do a linked list demo, or we can do something like strings, or we can do something else if, I don't know, if you want to type in the YouTube chat or something like that. So I think you should just be able to click one. I don't know if you can click many, but click the things you want to do, and whatever's got the most votes, we'll just talk about. I think it's 2 minutes. What are we going to talk about? 60 more seconds. What's been going on? Are you all no-lifing assignment 2? Is that the term? So bright in here. Oh, that works now. I can turn them off. It's not that sort of lecture, don't worry. Should I skip it now? Yeah, that'll work. All right. Well, that's close. Okay, clearly we want more time on linked lists. So that's clear. Maybe we can do a bit of both. We can do a recap of linked lists. We can do a walkthrough of the demo code, sorry, of the lecture code from Monday. And then maybe we can try and use the linked lists to do something more useful. Does that sound good? All right. Very clear signals there. Pokeball cards for that? No. I don't know what's going on with this computer. Hello. All right, why don't we power through? That'd be great. All right. Why don't we power through a recap of the topic? And we'll do a walkthrough of the code after that. Sound good? And if you've got questions on linked lists, if you've started, please, get them ready. You can ask them in the YouTube chat. Even if you're in the room, you can bring up the YouTube chat. If you get the link to it, you can ask questions, and Brianna, you can yell them out, and we can do a bit of Q&A on linked lists. Okay, but just broadly, I think this is now the third time we've introduced the topic of them. So hopefully, if you've been watching all the lectures, I apologize if this is repetitive. So a linked list is a data structure that allows us to store multiples of data. We know this. The big difference from arrays is that with arrays, we pack all of the data in the collection, next to each other in memory. Which means because we're packing it in next to each other, all we need to know where all the data is where that data starts, right? Whereas linked lists, it's a little different. We scatter each element around in memory and store a reference to where the next element lives. So the little demo that we sometimes do in the lecture room is an array would be this front row of people, 1, 2, 3, 4, 5, 6, would be the array. And all I need to know is where that row starts. And then if I go 5 over, I can find the fifth element, right? The fifth person. In a linked list, you can point to someone over here, can point to someone over here, and I can still follow and create a collection. But we have much more flexibility when we add someone to that linked list where they can sit anywhere. Whereas if that row is full, which it is, right, and that person needs to sit next to that person, we have to move everyone. Do you see that simple idea? And we store the memory address of where that linked list starts. And that's usually in a variable called head. The head of the linked list. That's a general topic, that's a general idea. There's only two components of a linked list struct at this stage. There's data structures that are like linked lists that store more data, but for our really simple case, we store the data and we store the pointer to another node. So it's a self-referencing data structure, or maybe sometimes called a recursive data structure. This idea I know trips a lot of people up. I think Jay was trying to get his head around it on Monday as well. This idea that we reference ourselves, right? This is a struct node, and yet in the struct node, we're pointing to another struct node. And I can see how that can send your brain haywire because you're trying to unpack this and figure out what's going on. I think the simple way to think about it is just to not overthink it. This is a pointer. It's not a struct node in memory, right? It's just a memory address to where another one of these nodes will live. I mean, that's it for the slides. Are there any questions? Nothing from the chat, but in the room?
Retrieving this data, what is each node called? Because they're all in the structure definition, they're all called next.
What is each? Say that again?
What is each node called? How do we refer to them?
What is each node called? Do you mean what do we call them, or how do we access them? So we call them elements, but I don't know if that's what you mean.
Like, do they have variable names?
Okay, this is a good question. Do they have variable names? Does each node in the linked list have a variable name? Is that sort of what you're asking? And I think we had a question similar to this on Monday. And the answer is pretty simply, when we create memory on the heap, how do we do that? Sorry? So let's look at the create node function here. This is responsible for creating a linked list node on the heap. What's the line here that is really responsible for allocating the memory? Yeah, line 130, the malloc call, right? That says, hey, I want enough memory to store a struct node on the heap, and it returns back what? What does malloc return? The memory address. It returns the memory address, right? That's the way we create memory on the heap. This is different from the stack, which is where you might be getting this confusion from. On the stack, right, if I say int x equals 5, this is how we create memory on the stack. And you're right, there is an associated variable. Variables are the way we create memory on the stack, or in a function, or at any stack frame. So we say, I want a data type with this name, and the program goes off and does that memory allocation. Somewhere there's probably a malloc call, something like that. But that's not the way it works on the heap. All we get back is the memory address. Now, in this case, I am temporarily storing it in a variable called new node, which points to where that memory address was, just so I can keep track of it and return it here. But I don't need to do that, right? I could just return malloc. Now, the data would be uninitialized, but there's no variable. There's no identifier for it. I need to keep track of what in order to reference it? The address, that's it. It's up to me if I want to associate it with a variable or not. Does that answer your question? So on the heap, there's no variables unless we put the memory address in a variable. Yeah. If you think about it, all variables are just memory addresses, really. You can get the address of a variable, and it's just associating it with an identifier. But good question. Any other questions? The individual nodes are actually pointers. No, they are the block of memory to store the data and the next pointer. But but they're just returning where they are. But they're still there in memory.
Sorry, yeah. I don't know if we've already covered this because I wasn't here last night, but so when we want to iterate through an array, so we have like a little counter that comes the array. So if you want to traverse through a linked list, how does that work? Can we cover that?
Okay, it's a good question. And again, we did cover this before, but I think it's worth talking about it. This is linked list 2. I think it was in linked list 1, but let me bring up my whiteboarding stuff. If you want, I can also, Brianna mentioned this, I can share this Figma board with you all. I think if you use an education email when you sign up, you were saying you can get, I don't know, something for free, but okay. So here is FigJam, has a new look, cool. All right, so here's an array, right? And remember what we said is key with arrays is that the memories, we know where the elements are because they're next to each other. It's contiguous, that term keeps coming up. So if I know where this array starts, because I've got a pointer to the memory address of where the array begins, and I want to access the third element, I just have to iterate over 3 times, or move that memory address over 3 times. So that's where this idea of the index comes from, right? So you're spot on. That's what makes arrays random access. Because I can just say, if I want to go to the 4th element, I know it's going to be here in memory. And I can go straight there. It's really efficient and fast and cool. Guys. Shh. This is a linked list representation. The linked list starts here. The next element could be anywhere in memory. I have no idea. Who decides where that element's going to be when it's malloc? The operating system, essentially. Wherever there's a nice bit of free memory that it decides is a good place to put it, it's going to put it. So I can't guess where it is. I can't say, well, the second element is going to be in the next position over. It completely depends on the call to malloc. So what we do have, though, is the memory address of where it was placed. So I need to dereference that memory address and follow it to the next element. I dereference that next memory address, I follow it to the next element. So there's a little bit more work in the dereference, but also in order to find the third element, I have to do 2 dereferences. If I've got a really long list, there's no choice but to dereference, 100, 1,000, 10,000 times, which is still pretty fast, don't get me wrong, because it's not a memory allocation call. It's just a dereference. It's pretty quick.
So instead of like how in arrays we just iterate through a counter and index, we basically be iterating through like dereferencing.
Yep. We dereference, we store that variable, and then we dereference that variable and store that variable in a loop. Yep. I've got the code to show you how that actually looks in C. But that's the idea of it. But these are really good questions. Are there any more good questions? If you're sitting there and you're a bit shy and you don't ask a lot of questions, but you do have a question, now is a good time.
What about you talked about the free function and how that prevents like memory leaks. Can you explain that a bit more?
So the idea, free is not specifically, associated with linked lists, but it's associated anytime we use malloc, basically. A quick way of thinking of it is anytime you malloc memory, at some point you've got to be freeing it. Because variables on the stack automatically free when we complete that stack frame. So the program itself is keeping track. But remember, malloc data lives there forever until we free it, or the program ends. But some programs are really long living. Like we spoke about that example of like Boeing airplanes. You can't shut down a Boeing airplane in a 12-hour flight. So if you've got a memory leak, which they do, the Boeing operating systems do have memory leaks. That's why in the operating guides, they say when you land the plane, shut the computer down. Right? So if you've got a memory leak in a long-running program, and 12 hours is not long, right? Server applications run for months at a time. So if you've got a memory leak, it's because at some point someone has mallocked data and they probably finish with it, but they forget to free it. So if I've mallocked a node on the linked list, and for whatever reason now I don't need that memory, that's maybe not a good example because it's part of the linked list, but it's just anytime I malloc data that I no longer need, right? I need to free it. I need to pass the pointer address of where that memory is to free. Any other questions before we look at the code? Is that a hand there? Yes. No, malloc gives us the exact address of where that memory was placed on the heap. Where does it say it? So if we look at this line, this is a use of malloc. Can you see that? We call malloc. How much memory are we mallocing? Yeah. However many bytes it requires to store a struct node is being mallocked. And it returns back a memory address that we're storing in new node. Why does this work? Because new node here is a pointer to a struct node. And we just mallocked a struct node. Or we mallocked enough memory to store a struct node. So we get back the exact memory address of where that memory was allocated in the heap.
So when you go back into main with the function, it will be returning the address?
Yeah, so here we store that memory address. We do stuff to the node in the memory, and we return new node. What is new node? The pointer. And let me look at the one in main. Oh, we don't call it in main anymore. But in the caller, for example, here, well, let me get another example. This is a good example here. So we call create node here. We know create node returns that memory address of where the new node was created. And here we assign it back to yet another variable called new node, and we hook it up in the linked list. So in this linked list, the current element that we're adding to, we're setting its next pointer to be the same memory address that was stored in new node, which was returned back from create node. So we're passing down that new memory address to do what we need to do with it.
Yeah. Okay, so we're using a current pointer at where we are instead of like taking the exact memory address. Instead of like getting the actual hexadecimal address, we're putting it which one we're talking about, and then doing that for it all.
Well, in this case, all we're doing is setting the next pointer of current to be that memory address. Current itself is also, a memory address to yet another node, the one before it. We're adding at the end. It's all hexadecimal addresses. We just put them in variables because it doesn't make any sense to deal with them ourselves. They're meaningless to us. I think whiteboarding. We could do some more whiteboarding today. Okay, there's a lot of, yeah, let me go here first and then I'll go to Brianna.
My question is a bit more of a curiosity thing. So the stack, is it basically a heap of memory that automatically gets freed?
The stack is not a heap of memory really. It's a portion of the RAM available to a program. A portion is the heap, which is this unmanaged memory. And then the other portion is the stack, which you could call it sort of more managed memory, although that's got connotations. And the idea here is that any variables created in a function get associated with a particular stack frame. And anytime we call a new function, automatically a stack frame gets generated, and any variables that that function needs automatically get allocated on that stack frame. So if you look at, if we look at the inserted tail function, anytime this function is called, we create enough memory for 3 variables. The int data, a pointer for a struct node, and another pointer here for current. And when the function ends, that memory is freed. But it happens on its own. All we know is we call the function ends. That all happens in the stack. Does that answer your question? Okay, and Brianna? Good idea. Okay, good idea. All right. So memory leak is any time we malloc data, we do something with that data, like we use it, we're storing something there. Here's an example. Let's say I go to, the Kahoot website. Chrome is a program. It's a very complex program, but it's just a program. And to render this page, which has actually got a huge amount of assets on it, you can look at all the images. There's JavaScript to get the carousel moving. All of that is stored in memory. Yeah? It's got to be stored somewhere. It's stored in memory. It's not stored to a file on the disk. If I close the tab, do I need that memory anymore? Do I need to store that Kahoot banner image? Or think of it this way. Imagine if I didn't throw it away. Every time I opened a website, everything that makes up that website would stay, we would run out of memory. Agreed? That's a memory leak. If Chrome didn't clean up after itself when we closed a tab, a lot of that data would be in the heap, by the way, because we don't know how big it is. That would cause a memory leak. Memory leaks are very, very common. You might think, how hard can it be to clear up data? But it is pretty tricky. So anytime we malloc memory and we finish using it, that's the key, but we don't clean it, we don't free it, we're in trouble. So if you look at delete, is it delete node, remove? Here's another way of, here's a good way of sort of explaining it before we go into leak checking. So here's the function remove at tail. What's its job? What's this function's role? We should probably annotate it. Remove, yeah. So say it in different words.
Removes the last node.
Yeah, removes the last node of a linked list. It has to traverse every element until you find the null pointer in next, then remove it. So that's the general idea of remove tail. The idea here is that whatever's the last element in this linked list, we no longer need it for whatever reason. Imagine if, look here, right? This is the last node in the linked list. Imagine if I never, sorry, here. We get to this point and we say, okay, well, I'm now ready to delete that node, that last node. So I'm going to set the second last node's next pointer to point to null, because it's now the end. And I'm going to free current. But if I didn't free current, would that still remove the last node from the linked list? You think no. Who thinks yes? Who thinks no? What does everyone else think? Come on, you got to pick something. You're like American voters. Who thinks this will delete the last node still? You have to put your hand up, or I don't know what I'm gonna do. Okay, and who does not think this will remove the last node? Jay, I want you to stick with your conviction. Good. Why don't we test it? Because we can just run this program. We've got some tests for it. So this is the, remove at tail. Here we go. So if we look at the linked list before it, the 14th node was the last element. We ran the remove at tail function, and look at that. It's gone. So you might be thinking, I'm the next Brian Kernighan. I'm the best C programmer in the world. No one can stop me. Google's going to give me a $1 million salary. Like, it's gone. It's clearly gone here. We traversed through every node and it's not there. And that makes sense because we set the previous node to point to null. But the problem is what? It's still there. It's still in the heap. We never freed it. That's a memory leak. And in fact, we're really screwed here. Why? We can never really recover from this memory leak because we don't know where that node is. And we can't actually find it. So Jay first and then you.
What's it got to do? Why is it called a leak?
It's a leak because okay, that's actually a good question. It's a leak because if I call remove at tail again, what's going to happen? Here we removed 2 nodes, but what's happened? We've lost 2. It's going to, and the idea is that, maybe I can delete all 5. I'm going to have 5 memory leaks. Well, it's the one memory leak, right? But it's a leak because it slowly grows the amount of memory we've lost, or that we're not able to free, like a leaking tap. And yeah.
What do you really mean when you say we lost the number?
We lost the reference to it. We used to know where it was because it was the last node in the linked list. So I could follow the linked list and do something to it. I could free it. I could add onto it, whatever. But I rearranged my pointers of my linked list. All right, if I go to Figma, what I did was, so this is the linked list. Maybe I'm going to move that here. It starts here, points here, points here, points here. What I did was I took previous and I pointed it to null. Do you see that? And okay, I guess I should probably just do this. Do you see how there's no reference to this node anymore? That's what I mean by lost. We have no reference to it. We have a reference to the start of the linked list. It has a reference to this node. This node then just points to null. So this is not leaked memory. This is not, but this node, we have no way to access it anymore. It's lost. That answer your question?
So, say you accidentally have a memory leak and you lose where the node is. Can you prevent that and free that up again if you close the project?
Yeah. So if you quit the program, all the memory gets freed. So it's not catastrophic. Well, it's catastrophic to your program if you run out of memory. Eventually it will crash. If you do this too many times, which in this case, this is a very small amount of memory, you would have to be running this program for a very long time for it to crash on a modern system. But you could be writing embedded code that runs on a very small amount of RAM. You'll crash. Yep. Was there another question? Here? No. All right. Okay.
You said about Chrome when you close the tab that it clears out all the memory, but don't you actually store some of the memory in cache?
Yeah, but we're not getting complicated. Yeah. Chrome does a lot of optimizations because it knows that you might revisit the site again. So it has a little amount of time where it'll keep it, but let's not bog ourselves down.
In the memory leak, so there's no way to like recover the memory in the program while it's running. But when you close it, you can fix the code and
When the program ends, all of the memory is freed. So it's not a problem for the operating system, really. It's a problem for you in your program.
what if while my program is running, it's almost like because the memory leak's running out of memory, instead of closing the program, I add more RAM sticks to my computer.
So yeah, you go to that buy more RAM website and then, yeah, I guess if you were to expand your available memory, I mean, think about it another way, right? Let's say you're about to run out of memory and then you close Chrome. That is the same thing. You're going to expand your memory. So yeah, you'll just continue to fill it up until you can't. Yeah.
You can free up the memory program and stuff, but it does take
Yeah. Yeah, I don't think you can hot swap memory. I don't know, maybe some machines you can. All right, so hold on. So the point I'm making here is if you, when we know that we're finished with some memory, we need to remember to free it at the point in which we have a reference to it. Right? Now, let's say we don't do this. Memory leaks been a long-running issue with programming and programs. This is a unmanaged language C where we do have these problems. Later languages came up with designs in which it's not really possible to have these sorts of memory leak problems with an asterisk, but there's also a bunch of tools designed to detect memory leaks. And in fact, one of these tools is built into DCC. So Brianna's just got to remind me how to actually run leak checking. Or Tim is. So when I compile it, right? So when I compile it, I can pass in this leak check flag to DCC. And DCC actually has bundled in some dynamic memory analysis tools, which we don't have to really talk about. And it just compiles the program. I run that program like normal. And it's actually able to tell us, even it tells us the line, which is pretty amazing if you think about it, that on a line 132, I had a call to malloc, but no associated call to free. So the line number might not be exactly right. It's telling us where that memory was created. It doesn't know where we should have freed it. That's for you to figure out. But this is a reminder for you to say, when I deleted a node, where's remove? I've got to make sure I free it. The reason we're still getting a warning here that we've not cleared the memory is because what this technically wants us to do when the program ends is something like free all the data remaining in the linked list. So you could iterate through each node and free it, basically. Or you could create a function that does that.
we have like free at the end of every single node we created, then why do we need to do this all over again?
Say that again?
We already
Oh, because we're not calling remove at tail every time. That's why. Right? So if I just said while I guess, what do? I can just do struct node I guess I need to do Wait, help me out here. Oh yeah, that's what I was trying to do. Yep. Yeah, that is what I was trying to do actually. Thank you. So while head is still a linked list node, remove it and return back the new head, and we'll keep doing that until head is null. And then hopefully, if that frees everything, we get no leak check message from the compiler, from the program. Now, it's kind of redundant here because this is when the program ends anyway, and the operating system will clear that data anyway. So it's a little bit redundant, but if you do have this cleanup at the end, you know for certain, or pretty much not 100% certainty, that there's no memory leaks in this program because it's been detected. So if you clean up after yourself really rigorously, you can know that for pretty much at this level of programming, there's no memory leaks here. With an asterisk. You can still trick these checks. They're not 100% foolproof, but they're pretty good. Pretty cool. So you can pass leak check to all of your programs that use malloc and figure out, are you being a good memory citizen? Are you cleaning up after yourself? Good stuff though. Any more questions? I'm not freeing every element. I'm only calling remove at tail, which frees the last node in the linked list. So I'm removing one at a time in a loop until they're all gone. Do you see that?
Do we just say the pointer's name for free, like the whole? If we want to delete something and then free it, do we just put the pointer?
You free the pointer.
Which one? The one that's on? Like the one that's going to be deleted.
Yes. The memory you want to free, you take the address of it and call free with that address. Is that what you're asking?
Yes.
Okay, good. All right, any more questions online maybe? Do we want to do, we didn't actually do a run through of the linked list code. Did we still want to do that? Yes? All right. I'll do it briefly. So essentially we have a bunch of functions that create linked lists, traverse linked lists, and clean up or remove nodes in a linked list. So the first one is the insert at tail function. Tail and head are terms for data structures like linked lists. Head being the first element in a linked list, tail being the final element, right? It's like an animal. The head's at the top and the tail's at the end. So insert at tail inserts some data at the end of a linked list. So what does it have to do in order to do that? Remember, we don't know how big a linked list is. So we have to traverse through every single element until we get to the end. Then we can insert the new linked list. So we create another pointer called current and point it to where head was pointing. Here we have a boundary check. What happens if the linked list was empty? The reason we need this is because if I just tried to iterate through and it was empty, I would be dereferencing the null pointer, and that would cause an error. So this is a boundary check to make sure that we've catered for the case in which the linked list is empty. What do we do if the linked list is empty? We just create that new node and return it. So there'll be a new linked list with one element in it. All right, but if we have some data in the linked list, we have to iterate current through each element until a node, its next address is storing the null pointer, which means if we go to our diagram, until, maybe I'll leave it like that, until this node, right, its next is storing the null pointer. That means we're at the final node. That means we can then add an element after it. And to add an element, all we have to do is malloc it and change the next pointer here that was pointing to null to point to that new node. That's what it means to extend the linked list. So that's all this while loop is doing, is changing current to point to next, next, next until the next one is null. Now we're at the end, and here this is that creating that new node. We call create node, which is doing a malloc. It returns back the pointer of that new node, and we say, okay, you no longer point to null, you point to that new node. That new node, it points to null because we've passed in null there. And then we return pretty much always the memory address of the head node, just so that the caller can go back to the start. Why do we have to do this? Because you can't go back in a singly linked list. There's no previous pointer, right? So if you lose track of where it started, you can't go back either. So that's why we assign that's why we create this temporary current variable. And that's inserting at tail.
Slightly silly and unnecessary, but could you include a second pointer in the node on the pointing backwards?
It's not, yeah. So the question was, could you do this? Or prev, maybe. Could you store also a variable that points to the previous node? And that is a great idea. And it's such a good idea that you're not the first person to come up with it. And it's called a doubly linked list. So each node stores its next address and the previous address. Why is that beneficial?
In case you have a memory leak.
No, you guys are memory leak obsessed. No, I don't think it's going to help with memory leaks. You're going to have the same problem. It's just because you might, if you've got really long linked lists and you're really far down a linked list and you need to go to the previous linked list node, you actually have to go back to the start and iterate all the way. Do you see what I'm saying?
So it's more efficient.
Yeah, I can just go back one. I have to do one dereference to go back. So it's more efficient if we're going back and forth really frequently. Think about, again, back to Chrome, the forward and back buttons. I always sort of explain that as I don't think it is a doubly linked list in reality, I'm not sure. But you can think about forward and back as a doubly linked list. I'm at a URL, I'm at a web page. I have the memory, I have the in fact, it's a URL, it's an address. I have the address of the forward in history page, right? You know, when you're on your shopping carts on Temu or whatever, and you're buying a bunch of crap, and you're going back and forth because you're like, should I spend this money? And then you go back, and then that website before it, it can go back further, or it can go forward. So if you're doing this frequently, doubly linked lists are quite useful. But there's always a cost. What's the cost? You said it, I think. Say it. Memory, you have to store that previous pointer. Again, in 16, 32, 64 gigabyte memory, that's a zero cost essentially. But on really small embedded machines, that could add up. It's what is it? A pointer is 8 bytes on a 64-bit machine. It adds up.
Don't most machines have enough memory to like?
Well, most machines like this do, but not microcontrollers that you're sending to the space station.
Not your TV remote.
Not your TV remote, exactly. Paid actor over here. So but if you look at all these functions, right, here's what I want you to understand. So we had insert, what did we just ran through? Insert at tail, yep. There's only like 3 things you can do. You can traverse, you can add to the next, and you can remove. That's pretty much it. Like if you look at remove at, no, let's look at remove at tail. It's like exactly the same code. In fact, you could probably break down some of these functions into smaller reusable functions, like traverse to end. You get back the pointer of that node and then you free it, for example. But if you look at remove at tail, again, you have the empty case that looks an awful similar. You iterate, There's a one more boundary case for removing, and then you just remove. It's the same idea. For removing, we need to not only store the current node, we need to store the one before it, because we need to hook that next up to something else, right? That's all. That's why we have this line. But the core ideas are exactly the same. It's the same with even inserted index, right? Inserted index, which is inserting a linked list, a node basically in the middle of a linked list. Same idea. You've got to get the linked list, traverse until the point you want to add, and then you just rejig the pointers, the next, right? You have your empty case, you have your traversal, and all we're doing in this traversal is also keeping count of how many times we traversed, so we can make sure we can count if we're up to the right position. We have a boundary check again, and we just do some pointer rearrangement. Same idea. So they're still quite simple data structures, but because we're dealing with pointers, we're dealing with memory, it can get confusing and things. But it's been really great questions so far, and everyone seems in a lot better spirits today. What's happened? What was wrong with Monday? Just the weather and the Mondays? Yeah, I guess, yeah. We're not the first to experience that. All right, lecture break, coffee break. Come back. Hello? We're good? Okay, great. All right. Tim's doing everything here, working hard. So is Brianna. And I guess John. Okay. God, you guys are in a great mood today. I don't know what it is. It's me. Yeah, sure. It's the CSC barbecue and the sun. All right, so 50 minutes remaining. I think we've spent enough time recapping linked lists. Guys? Quiet. So we've got a couple of choices, I suppose. We can do a sort of quote unquote practical linked list demo. One of the ones I sometimes do is URLs, like a web browser history. Or we can do an exam style linked list question. You want to do that? All right. How exciting. Okay, so let's think here. Exam style linked list question. We just wrote them for the real exam coming up in a few weeks. So maybe something here, I don't know how achievable this is in the next, oh, it should be fine. Why don't we do something like this? So given two linked lists already formed. Now, often in the, guys, please keep the noise down while I'm sort of ranting. Given two linked lists already formed, so often in the exam questions, you will be passed in the data, right? And don't worry, there'll be an entire practice exam session with the same sort of structure. So given two linked lists, we can say maybe to assume same length, so same number of elements in linked lists, create a new linked list which stores the, you could say the sum of both linked lists. This is a pretty classic, I think, linked list hurdle 1 question, right? Angela? Yeah. So let's just, before we go anywhere near writing code for this, let's think about a couple of things. Conceptually, is there anything here that's new or going to cause us trouble? Everyone's silent. Good. Okay, yeah. I mean, this is very brief. So the sum of both linked list elements. So if you've got like 1, 2, 3, and you've got like 3, 2, 1, it would store 4, 4, 4. That's what I meant. Usually in the exam question, like always in the exam questions, you'll get an example, really clear example like this. That's like really simply, what should this be doing? We don't want you to be confused on what you should be doing, right? Maybe how to do it can be complex, but. So you might need to iterate through two linked lists at once, sure. But we know how to iterate through a linked list, so there's really nothing new here. And we'll look at ways to do both. But really what I was getting at is that there's nothing that we don't know how to do. We know how to sum two numbers. We know how to iterate through a linked list. We know how to create a linked list, right? Nothing crazy. So let's use our linked list program to, you know, did I not have this open like that? So we're going to use our linked list program to do this. what I will do quickly in main is to create 2 linked lists. Right? Let's just do that. So we got linked list 1's got 1, 6, 8, 10, 12, 14. Linked list 2's 1, 6, 8, 10, 12, 14. We can change, I don't know, maybe just a couple of these. Right? Just so that they're different. In the exam style questions, you won't see construction of initialized data like this. They're usually passed in from standard input, but it all happens automatically. The end result being you might have 2 variables, like in this case, one called head 1, one called head 2, or linked list 1, linked list 2, with the data already in them. So our task would be, maybe it might be to create a function called create, linked list sum that returns back the head pointer of a new linked list in memory, right, that has the sum of each node. Does that make sense? And we would even give you typically that function declaration. It'll already come with the program. So it might be a struct node pointer to create, or maybe some new linked, maybe let's call it some linked lists. I'm going to give, that's a really long title, but I mean, it's a good title. Back off. What would it need to accept? It would need the struct node linked list 1 and the second one. Yeah, I've gone way over the character limit line. Did anyone read that book I suggested? Oh my god, now my formatter is all... Why do I bother? I said, I actually, on the weekend, I went back home to Melbourne and I was talking to this, I met some friend, had new friends, and I was like I was like, you look really familiar. And I was like, did you go to some uni that I used to teach at? And he's like, yeah. I was like, oh, I think I might have taught you in like intro programming. And he's like, oh, to be honest, like as soon as I finished, I just lost everything. I was like, yeah, that's exactly what we want to hear. That makes me feel great. Okay. I don't know what's going on with my formatter here. We tried to fix something with it earlier and then something's gone. Okay, but we get some struct, something like this, and we go ahead. So I guess everything we do it in here. Maybe I could just, how's that? So we just got to fix it up here. Anyway, in the book that no one read, he talks about don't be scared of long expressive variable names. Because some linked lists doesn't actually tell me that it should return back a linked list, although that's in the type. So you could argue that it is self. But anyway, okay, we're getting off topic. All right, so what do we have to do? Let's think about it. We have to iterate through each node in both lists, add a new node to the new list containing the sum. Return, the new list head pointer. That's roughly all we need to do here. So why don't we try and write this somewhat collaboratively? So why don't you guys tell me what to do? What should we do? Sorry, let me just get this. That's like construction. Okay, what were you saying? So create like a current pointer for the two linked lists. Yeah, I agree. We could also probably create the new linked list. Yeah. But yeah, those three things sound right. So let me do that. So current. So, well, let me do this first. And what would we assign to the first current? Someone else? Which would be what? What do I type? You're right. You're right. Yeah, linked list 1. That is the head of the first list. And for current, for 2, I can assign it linked list 2. And then I might also create struct node new linked list maybe. That's a bit more specific, correct. Now keep in mind we'll have to think about edge cases. So what if both the linked lists are null? What if they're empty? That could be an edge case. But we always give assumptions. Did I just lose the, where was my note with the, anyway. Oh, it was here. We've given you the assumption, so you can safely assume that the two linked lists will always have the same number of elements, right? We're not ever going to do a gotcha on this where we'll pass in different lengths then. If we give you an assumption, it's a safe assumption. But maybe, you know, a harder linked list question might not have this property. So you could have different sized linked lists. Maybe you just add 0 to it, you know, and fill them out. But for now, we've got the same linked list lengths. Okay, I'm over here. Yep. Where was I? Some linked list. Okay, so I've done some initialization. That's looking good to me. So for now, let's not worry about the edge cases. Let's just do the first thing we need to do. Oh, I guess maybe we should look at it. Anyway, so we have to iterate through both linked lists. We know they're the same size. So what do we, oh, do you guys want to tell me an idea, or do you want, anyone got an idea? The thing is, so you said, can we dereference both of the linked lists, current 1 and current 2, and then create it? But the thing is, we'll have to do that many times. So we need to think about the while loop is essentially the idea here. So if we just had one while loop and we want to iterate through every element, we can just say while current 1 is not equal to null and do that. But we've got two linked lists here.
Can we do like a current I and then increment I every time?
Current I?
Like, you know how with arrays we have like
Gotcha. So the question was, can we do, so with arrays, if we had two arrays here, you're right. I would say int I equals 0, I++, and I would access I in both elements. We can't do that here because we can't offset each linked list by an integer to get the second element, because we need to dereference each one separately. So really what we need to do is combine both dereferences in one loop here. And because they're the same length, we can do that. So we can say while current, there's a few ways to do this, but here's one way. So while current 1 is not null, technically, because of the assumption that they're both the same size, I could actually leave it there. Because if current 1 is not null, neither will current 2. Does that make sense? But it's probably better to put it in. Whoops. While they're both not null, Oops. My format is all over the place now, but we iterate each one. Remember, we have an AND statement. So if this is true, and this is true, we do both of these things at once in one loop. So this is iterates both linked lists here. Checks that we lists. All right. Now we need to do something every time we loop, right? Every time we have current. What is it that we need to do? Sorry, I'm asking this guy. Oh, so we need to add the two integers, is that what you mean? Okay, we can actually start by doing that. That's great. So we can say int sum is equal to current one data plus current two data. So we have the new value that we're going to store in the resulting linked list. You had your hand up. What do you want to do next? Create a node. How do I do that? We can use the functions that we have here. We've got two ways to create a node. If we think about this code so far, we have create node, which creates an individual node, but we have insert at tail. Doesn't that sound an awful lot like what we want to do? We have a linked list. Maybe there's no elements in it, or maybe there are, and we want to add a new element to the end, storing the sum. So we can use insert at tail. Again, in an exam style question like this, we might give you some functions like insert at tail, because we're not testing you in your ability to write insert at tail. We're testing your ability to use linked lists. So insert at tail sounds really good to me. Now, you guys tell me what do we actually do with this function call? There's a few things we need to do. Pass the sum. So if we go to insert at tail, the first thing it needs is the data that we're storing, and you're right, it's going to be sum. Beautiful. What do we pass to the second parameter? The head. AKA, which linked list are we adding to the head of? Are we adding to the tail of? Someone new? Yep. New linked list. And we will, to be good citizens, assign new linked lists back to that result so that we get the head assigned back into it. You know, actually, I think that's it. I don't think yeah, we don't have a boundary case for the null in this case, because if the linked list is null, the loop will never run. Therefore, new linked list will be oh, there's one thing I'm missing. Someone yell it out. Just scream it. Just scream anything. What are we forgetting to do? Not free. Return it. We never returned new linked list. So at the end of the program, after the loop ends, we need to return new linked list. Right? New linked list being the head, right? Because insert at tail returns head. So it's going to return the head of the new linked list. All right, let's see if this actually works. Oh, we have to call it. So here I'm just going to print out the return of some linked lists, because it returns the head pointer. And what should we see? Well, let's find out. Thank you. All right, does that look right? 1 plus 1 is 2, 6 plus 2 is 8, 8 plus 8 is 16, 10 plus 0 is 10, 12 plus 1 is 13, 10 plus 4, 10, oh my God, 14 plus 10 is 24. That's good, that's it. Now, assuming you account for edge cases, so why don't we do that just to make sure? What if I pass in? Oh, well, that's not print. Print. What do we expect that to print? Someone said it here, roughly. No? Maybe not? If I have two null lists, what will it should do? Well, it will return back a pointer to where? To null. And I think is print going to handle that? Yeah. We just get back null. That's it. We would have a bunch of auto tests that you can run while you're writing your code to check that it's working. And when we do marking, we sometimes have hidden tests just to test a few edge cases, a few different values. Really, if hidden tests are only there to make sure that you don't hard code all the cases. So we throw a bunch of extra cases, we run the auto tests, and you're on your way. So just to give you a reminder, for hurdle questions, you need to get 50% of the auto mark test results. Right? But that's a pretty consistent linked list hurdle one. So do you all think you could do something like this? Oh, okay, all right. Is this an online question or a you question? Okay. So Brianna's just asked, should we look at the edge case where maybe the two linked lists could be different lengths? Which I think is a nice little extension here. I can't remember if, Angela, an array linked list total one, would it have same length or could it have different lengths?
It could have different lengths, yeah.
Yeah, some of them could. Okay. All right. So this was, just to remind everyone, this was with the assumption, just remember to shut the door, please. This was with the assumption that both linked lists always had the same number of elements. What if we lose that assumption? So what if the two linked lists could have different lengths, which means one of the linked lists will end before the other. Now, the first thing we need to understand is what is the expected behavior? And this is where reading is really important, right? You need to read the question and the spec to understand what we intend for you to do. Because there's multiple things you could do. You could say, well, if they're different lengths, we just don't do it at all. We could say, well, if they're different lengths, add 0. But maybe we'll say if they're different lengths, add 10. Like, it's up to the spec. So you got to read. So somewhere in the spec, it'll say, if the lengths are different, what's a reasonable thing to do? Add 0, I think, for the missing one. So, and then there'll be an example. Whoops. Right, so that's an example, whereas this one just points to null. The result should be 4, 4, 4, 5, 6, null. So now is the spec clear? Yes, I think that's pretty clear. Does that change what our function's going to look like? What do you think? Someone said no? Well, we can test it, right? So what did I say? Why don't we add 2 more nodes to the second linked list? what's going to happen? Who's got this program in their mind's memory well enough to give me an answer? What's going to happen? Oh, Jay thinks an error, but that's so pessimistic of him.
I think it's cut off at the point where
I think it's going to cut off too. It'll cut off where the earliest linked list ends. So it's only going to sum up and return the minimum number of nodes. The reason for that is we have that while statement that loops until either one of them, because it's an AND statement, hits null. So as soon as one of the linked lists hits null, right, the other one will also stop traversing. They both stop traversing. Let's verify that. Whoops. Oh my God. One goes to 14. One goes 1, 2, 6, 8, 14, 10, 10. And this is doing the sum of only up to 24, right? So this 10 and this 10 are missed, which is what we expected would happen. Maybe to make this a little easier to read, I'm going to get rid of any double digits. Because then they're always going to be the same. Whoops. They're always going to be the same. No, they're not, because it's not a, oh, because this is different. Okay, cool. Is that clearer? I don't know. Oh, there's still a 6. Oh, because now, yeah, oh my God, I give up. You get the idea. It's not summing up that one and that one. All right, so how could we change this sum linked lists function such that, what should it do? It should iterate. Sorry? Iterate until they're both null. Yeah, that's good. Iterate until they're both null. But that's going to...
I think you can probably use an or statement, and then if one of them is null, you can just...
Yeah, I think that's the simplest solution here is we use or. The problem is though, it'll try and dereference the null pointer.
I think like, yeah, if you can check like if it's kind of different, dereference a null pointer in like an if statement, it just...
Yeah, I think you're on the right track. I'll repeat what you've said in a second, but let me get a few more suggestions. Another loop. So the suggestion from this student was, are you saying within the loop? After the loop? Ah, that's a great suggestion, actually. I really like that. So the suggestion, so there's a couple of ideas. Let's be frank, let's be on, not frank, whatever. There's more than one way to solve this. More than one completely valid way. I could change it to an or statement. This was the solution here. I changed this to an or statement. So only either one of the sides needs to be true. So it will keep looping if there's data in one of the linked lists, but I will need to add an if statement within the body to check that I'm not dereferencing null for either list, because we don't know which one is longer. The solution here was keep it the way it is, loop until one of them hits null, and then check which of the linked lists is not null and just add that on. And I kind of really like that. I think we can do something actually quite cool here. So I'm going to do this solution.
I have another thing to add to this solution.
Yeah.
So what if you do like a while loop for the first one, like current one until it becomes null, and then you do another one, the current two until it becomes null. That way they're both two separate while loops and it doesn't interfere with one another.
So that was much more dramatic than I intended it to be. And that's just coffee, there's nothing else in there. Loop once. Okay, so I think the idea works. in the first, so what you're suggesting is to separate the two statements and loop and iterate them separately. So I think what you would do the first time is create the new list and you add the new elements, setting it just to be data. And in the second loop, you add current to new links data. I think that also, but then you would also need to potentially add new nodes. So it would work, but I think it's messier. Because what if linked list 2 is longer? Oh. I like this idea. So what was your idea? So leave this the same. Help me out here. Do you want me to duplicate this, by the way, so that we keep this version? Yep. So I'll make a new function. Does that sound good? Now we're going to give it a new name. I'm going to go wild here. Some linked lists, jagged. Does that make sense? Jagged being they could be different lengths. All right, so we do this. That's untouched. That's what you're proposing. After the loop, we can say if current 1 is not equal to null, we would need to add new nodes to new linked list. I think we can say else if current 2 is not equal to null. Add those nodes to the linked list, basically. Does that idea make sense? And only one of those can be true, because for the earlier while loop to end, one of them had to hit null. So only one of we don't know which condition, but only one of these conditions will be true. I'm going to give maybe the straightforward solution, and then I'm going to give the smart-ass Jake Renzella solution. Does that sound good? So if we're here, I think all we do, oh, in fact, that shouldn't be if. What should it be? No? While. Yeah, who said while? Yeah, very good. Why? Because we can just iterate. We can just iterate here. This is the. Does that make sense? So we make this a while loop, and then in actually here we just make this a while loop too. And then we just do this. Does that make sense? Does that make sense, everyone? So we loop until one of them ends, and then we just loop a few more times on one of the linked lists. Let's test it out with the jagged. So this should be, that doesn't seem to work. Sorry, I got to do that there. So 168.111, 128.0.1111 becomes 2, that's right, 8, 16, 1, 2, 2, 1, 1. Yeah, that's pretty good. I think that checks out to me as a nice solution. So yeah, well done to you. That's a nice solution. Yeah, because we've got nothing to sum it to, so I'm just creating a new node with the data of the non-empty linked list. Yep. Okay, I said there was a smart-ass solution here. Anyone have an idea at what I'm getting at? Come on, someone online. There's an idea here that we can, I think, would work. I'm not actually 100% sure. One of the tutors?
You're going to find
Yep. I'll just do it and then you'll see. So let's actually change this to if. Is that it? Or is it next? That's it. Yep. Let's just test that it gives the same result. What's gone wrong here? No, because current 2 should already be at the end. Ah, yes. Yes, you're right. Damn. That's kind of annoying, isn't it? I'd have to keep track of the last element, so I guess I could do like right. That's not gonna work, is it? What do I assign it to? But because it'll be, but won't it be the head still? Yeah, it's all head. Okay, the idea doesn't work. I would have to iterate through again, which I'm not going to do. Okay, screw you, Jake. I'm going to just undo that. Yeah, yes, yeah. But I'm just going to go back to the way this was. But the idea I had was that if I kept track of, this is why I said it was a smart ass idea, because that's what happens when you try and be too smart. But if I kept track of the tail of the new linked list, I could just add onto it the rest of the linked lists. So I didn't actually need to do the sum or create new nodes. So you're like, your new linked list would just point back to the original linked list that was longer, which is kind of nice because it's a bit more efficient. But I didn't keep track of the right things I needed to get it to work. Someone could come up with that at home. Again, if you write something like this, make sure that you test for the null case, which we are doing anyway, so that's okay. Maybe it won't be sum, maybe it would be a multiply, maybe it would be an average, but that's really straightforward to do. You just, instead of adding it, you just multiply it or something like that. Any questions? I'm not going to start a new demo for 4 or 5 minutes, so shall we just end early? Where are my slides? I'll leave the feedback form up. So really, you've got a few weeks now to start thinking about, can you do a linked list question like that? Right? I think you all can. I know you all can. But start thinking about that kind of stuff. Obviously, we had the assignment 2 live stream, so make sure you watch that. Make sure you keep on touch of emails, the forum announcements, revision sessions, help sessions. What else? All right. Have a great week and weekend, everyone, and I'll see you Monday for week 9. You got it working? Good job.